Okay, hello everyone. So I'm back with a higher level paper 1 IB physics, 40 marks. This is the mock exam that I gave my students. So I put together all these questions from some old past papers. Let's just get started. First one is a unit conversion. Should be relatively simple. We have joules is Newton meters, and a Newton is kilograms times meters per second squared, and then times meters. Kilograms cancels out and we get meters squared per second squared. Okay, next one, raindrops are falling with a constant speed during the later stages of the descent. So constant terminal velocity, right, terminal speed, and we should sort of know very quickly that that is when the air resistance is balancing out the force of gravity. And yeah, you can sort of pretty easily rule out the others, but this one you just have to quickly know. Okay, an astronaut is dropping an apple where the acceleration due to gravity is 1/6. The time it takes for the apple to fall to the ground compared with an apple dropped from the same height on Earth is. Okay, so it sounds like a suvat. So let's just remind ourselves that we have this. Something is dropped from rest, then it changes its displacement in this way. And we can just rearrange this to see that time is directly proportional to 1 over root g. Okay, and we are sort of modifying g here. So we're saying if g is 1/6 of g on the Earth, well then the time should be root 6 times larger, right? If you replace g by 1 over 6g, you get a factor root 6 up in the numerator. So time increases by a factor root 6 because time is directly proportional to 1 over root g. Two stones dropped from the top of a cliff, one straight up, the other straight down at the same initial speed, okay? So this one confuses people normally, but let's take a look at P. So what's going to happen, it's going to fly up and then it's going to start flying down again. And since air resistance is negligible, then when it passes its starting point, it has the exact same speed as its launch speed. It's just pointing down now. And of course, that's completely the same situation that we have with Q, where these two balls now have the same speed pointing down, released from the same height. So they're going to hit the ground with the same speed. Okay, so here we have an acceleration versus time graph. They've sort of shaded this area for us. It's a spaceship that's accelerating. It's initially at rest. What does this area represent? Well, we have to remember that the area under an acceleration versus time graph is the change in velocity. But if it was at rest to begin with, then the change in velocity is basically just the velocity it then has at time t. So, and this is all sort of positive, and it started from rest, accelerated in one direction, so it's basically just the speed it has when time is t. Here we have the velocity that is changing with time in this way. It's a truck. What can be deduced from the graph? So I like this problem. This is one of the more recent ones. Well, we should, definitely see that it is not always moving because it's zero, of course, at some point. It's also not moving in one direction because it has positive velocity and then later negative velocity. Displacement after time t can't be zero because we have sort of a larger area on one half of the graph and then a slightly smaller negative area. So that's also not true. But I mean, initially you should also all have noticed that, well, it is always accelerating because acceleration, as we know, is the slope of the velocity function. And at any given point, we have a slope. Okay, when it crosses the line, it's not horizontal. So at any given moment in time, we have an acceleration. The acceleration is always negative. Velocity is decreasing, going from positive into the negatives, but there is always an acceleration. Okay, so isotope of strontium, the mass is the order of, just have to do sort of an power of 10 estimation. So we have to remember that the mass number, 92 up there, the nucleon number, is the mass of the atom, approximately the mass of the atom in U. And then if you can't remember what a U is, you look it up in your data booklet. And you get this, and then you can see, well, this is approximately, well, 92 is approximately 100, 1.66 is approximately 1, and then you're basically just left with this, which is that, and the others don't come close to that. Electron volt is a unit of, that should be a fast one. You should know that that's, of course, just another unit of energy. If in doubt, you have to go to the definition. What is it again? Well, it's the energy gained by a charge of 1e, which is 1.610 to the negative 19 Coulomb, when such a charge accelerates across 1 volt. And 1 volt is 1 joule per Coulomb. So you get units of joules, right? So 1 EV is therefore 1.610 to the negative 19 joules, yeah? We have a spring being compressed by an amount E, held stationary, and then sort of released, right? So we know that when a spring is compressed by an amount E, we know there's some elastic potential energy equal to this. That was a K in there. And that is going to be equal to the kinetic energy of big M when big M leaves the spring, right? So we just have energy conversion. So all that stored elastic potential energy is going to be converted into the kinetic energy of the big mass. So basically V is going to be square root of this, and then square root of E squared is E, and we get A. Okay, on to thermal. Some calorimetry here. Small object of mass m at 100 degrees Celsius placed into the equal mass of water, and blah, blah, blah. Assuming there are no energy transfers to the environment, final equilibrium is. Okay. Well, something is losing energy, something is gaining energy. Now, the hot object is going to be losing energy, and it has a mass of m. The specific heat capacity of it is half that of water, so let's C be for water. And then the temperature change, it starts being hot, and then it reaches T at the end. That's the final temperature. So it's losing all that energy, but all that loss in it, all that energy is being gained by the water. Water has mass m, has a specific heat capacity of C. Temperature goes from 0 to T. So let's write it as T minus 0, just to get all the signs right here. Positive quantity equals to a positive quantity. And then we can see M and C cancels out. Basically get, well, we could do it like this. I can just multiply by 2. So I get 100 minus T equals 2T. 100 equals 3T. And then T is going to be 33 degrees Celsius. Okay, ideal gas. Enclosed gas, 27 degrees Celsius at a certain pressure. Let's call that P1. And it's at volume, V1. Gas volume is doubled. V2 is 2V1. And we have a temperature, T1, which is, let's quickly convert that to Kelvin so we don't make that mistake. 27 plus 273 is 300 Kelvin. Okay, so we want to now restore the pressure to its original value. We want P2 to be P1. How must the temperature now be adjusted? Okay, well, we basically, we have a lot of changing quantities here, but we know that as long as we have the same number of moles enclosed in this piston, which we know we have, then P1 V1 over T1 is going to be the same as P2 V2 over T2. And we know that P2 wants to be P1, V2 is 2V1, and we want to find the temperature T2. So P1 cancels out, V1 cancels out, and basically the second temperature is going to be 2 times T1. And T1 was 300 Kelvin, so there's going to be 600 Kelvin. Where's 600? Well, we have to convert it back to degrees Celsius. That gives us D. Okay, then we have this one, which is related to the formula that the average kinetic energy per particle is directly proportional to the temperature, right? So here we have some helium and neon mono atomic gases, and they're at the same temperature. So we know that the ratio of the kinetic energies is the same. So basically we can write that half m, and that could be for helium, the smaller mass. So the smaller mass has to have the larger velocity in order to have the same average kinetic energy. So let me write the velocity as a big capital V, and that's sort of the average of the square of the speeds. We don't want to get too technical with that. And then, so that kinetic energy per particle has to equal the average kinetic energy per particle for neon, which has a bigger mass, so it's going to have a smaller speed. So the half cancels out, and we want to find the ratio of the average speeds of helium, big V to small v, and that is going to be the ratio of big M to small m. And we know that the big M mass number is 20, small mass number is 4, so that's a 5. And then we take the square root to sort of get the ratio of the average speeds of helium to neon is root 5 to 1. There you go. Okay, waves. We have a surfer is out beyond the breaking surf in a deep water region. Ocean waves are sinusoidal. Okay, something like this. Crests are 20 meters apart. That's of course the wavelength. Rises a vertical distance of 4 from a trough to a crest. We have like 4 meters, and it does that in 2 seconds. Okay, well if it goes from the trough to the crest in 2 seconds, well, going back to the trough is then 4 seconds. That's going to be the whole period, which means the frequency is 1/4 hertz, and the speed, okay, wavelength times frequency. I didn't have to convert to frequency, but it's just a habit. 20 times 1/4, and that's 5. We could just have done, of course, that it's lambda over a period. 20/4 gives you 5 as well. Okay. Longitudinal wave. And we have air particles at a given instant of time shown here. Now we need to remember that, well, one wavelength is just the distance between two wavefronts that are sort of obviously shown there. So from Q to R, that's where we have one wavelength. You know, from a compression to an expansion to a compression, again, that's one full wavelength. So Q to R. Okay, polarizers. 30-degree angle to each other. So this one over here, we have sort of an angle of 30 degrees there. Okay, we have unpolarized passing through the first one. Now that means on the other side we have an intensity that is half the original. Remember that, unpolarized light going through a polarizer, the intensity halves and it gets polarized, right? So now the light is going up and down along the axis. Along the axis of the first polarizer. Okay, the emergent light, so Malus's law, right? Look it up in your data booklet. It is the incident intensity, which is 1/2 I1 in this case, times cosine squared of the angle, which is 30 degrees. Now they give us cosine 30. You should of course also know that. Root 3/2 is squaring that, 3/4. So I get 3 over 8 I1. That's what I2 is. So what's the ratio? I1 to I2 is 8 over 3. Organ pipe, length L. Fundamental standing sound wave is set up so we know that we have this situation can be represented by this. We know that we have quarter of a wavelength trapped in there. And what is the wavelength then? Well, it's 4 times the pipe length. Easy one. Charged oil drop between 2 parallel plates. So here's a little oil drop. Okay. Okay, now we adjust the potential difference. So we're basically adjusting the electric field so that it's at rest, which means that we have sort of a weight that is balanced out by an electric force. Okay? And then if the oil drop suddenly combines, coalesces with another uncharged oil drop, then well, what's going to happen is that the mass is going to increase, weight is going to get bigger, but the electric force is still the same, so it's obviously going to move downwards. It's going to be heavier, and the electric force doesn't change. So we have a voltmeter now that has a large resistance. Okay, voltmeters typically have very large resistances. But if they are also then put in parallel with very large resistances, then we cannot assume this voltmeter is ideal. So this is not an ideal voltmeter. Okay, so you have to sort of think of it as a resistor. And what is the reading on the voltmeter? Well, I can see 100 kiloohms, 100 kiloohms in parallel. They sort of combine to 1 over 100, 1 over 100, 2 over 100, flip it, 50 kiloohms. And then I have 2 resistors that are in a ratio 200 to 50. That's a 4 to 1 ratio. So the 5 volts are going to get divided up in a ratio 4 to 1. So that's 4 volts to 1 volts. So across the parallel connection, we're going to have 1 volt. And that's going to be the reading on the voltmeter then. Okay, particle, charge particle. Use your favorite hand rule. Okay, my favorite one is the right hand slap rule. Fingers in the direction of the magnetic field lines into the paper. And then I can see, oh, if this was a positive particle, then it would be spiraling the other way. So I use my hand rule to find out that it can't be a positively charged particle. It has to be negatively. Is it slowing down or speeding up? Well, it's spiraling inwards because it's losing energy, which of course means it slows down. So it's pretty obvious that it should be slowing down. But if you really want to maybe work it out in detail, remember that we get this expression for the radius of circular motion of a charged particle in a magnetic field. And you can see that the radius decreases when v decreases, right? If m, q, b are constant, then a decreasing r means a decreasing speed, so it's slowing down. Okay, highway entrance is designed for cars moving at that speed. Okay, now remember, so this is of course circular motion, right? So you have a car that comes in here and it moves around in a circular motion. There's a centripetal force on the car, which is the friction between the tires and the road. And that friction force is providing this amount of force, okay? Now, if you want to design a similar road for twice the speed, but if this force has to be constant, right? So the tires and the road doesn't change, the friction force is this. So if V doubles, how does R have to change in order for this to be the same? Well, because V is squared, R has to quadruple to give you the same force. Okay? So when V doubles, R has to quadruple to get the same centripetal force. Okay, so we have uranium-238 decaying into protactinium. Which one of the following pairs of emissions could describe? Well, you can see the mass number goes down by 4, the proton number by 1. Well, it definitely looks like there's some alpha involved because mass number goes down by 4. So A and B are clearly not going to cut it. And then alpha, would give us a 2349T, and then of course a beta, if it's the beta minus decay, we're going to increase that proton number by 1, so that seems right. Okay, so here's a really tricky one. I remember that causing a lot of problems. We have small particle with a mass and a charge entering a mass spectrometer at speed v. So remember, mass spectrometers are used to sort of distinguish small masses, right? You know, this is how we measure the mass of isotopes, because remember the equation I just wrote up, that when a charged particle moves into a magnetic field, it moves along a circle and the radius is proportional to mass. So if they all come in with the same velocity, then tiny differences in mass is going to show up as small differences in radius. And that's how we measure isotopes. So let's see. So we have now a second particle also moving inside the mass spectrometer. The second particle moves with the same radius, has the same radius. But what of the conditions then apply to this situation? Well, so we need the same radius. So we can see that, well, A definitely doesn't work. But then B, if I have twice the mass and twice the charge, well, then, you know, mass is in the numerator, charge in the denominator, so the 2's cancel out. Same speed, well, that seems to work for sure. And then we could just move on. But then maybe you would notice that C seems to work as well. You got the 2m twice the mass but half the speed, and then you kind of get the same radius. However, it doesn't move into the mass spectrometer with a speed v half, because charged particles that go into a mass spectrometer, they have always first gone through a velocity selector. And the velocity selector is a region where you have a magnetic field and you have an electric field, and they are adjusted so that the charge moves undeflected, which means that they have a speed given by the ratio of the electric field to the magnetic field. So all the particles moving into the mass spectrometer, they have first been selected by their velocity, their speed. So they're all going to be moving in with the same speed, so that's why C doesn't work. That's a bit tricky. Okay, so which type of radiation have discrete energies? You just need to remember it's alpha and gamma that always come out as discrete energies. Beta decays, you know, the electron and the positron are always accompanied by a neutrino, so they share the energy, and that's why we can have a continuous range of energies for electrons and protons. So this is B, only 1 and 3. Okay, so here's a homemade nature of science question. We decide which scientific theory is the best based on not this person who speaks the loudest, luckily, not by, you know, democratic consensus or people just telling us that it's the way it is. We also don't sort of allow opinions to be too speculative. Well, we allow for speculative opinions, but the way we decide which theory is best is we have to collect empirical evidence. That's how science works. All right, topic 8. Methane and carbon dioxide are both greenhouse gases believed to cause the reason for global warming. You know, what do these gases do? Well, do they absorb incoming radiation from the sun? Not so much, because that's mainly UV and visible that comes in. So that's really not the issue. Does it transmit the incoming radiation from the sun and the radiation from the earth? So, well, it does transmit the incoming, but it doesn't really, transmit the radiation from the earth, because from the earth we get infrared radiation, so it's not transmitting that. That's actually the whole issue, and that is why D is the correct answer, that it transmits incoming radiation from the sun, mainly UV and visible, but it absorbs the outgoing radiation that is mainly infrared, and re-radiates that back to the earth. And yes, reflecting incoming radiation, well, actually methane and carbon dioxide are maybe not really responsible for the reflection. This is sort of cloud cover and sort of just, you know, the surface in general just reflects radiation off. So that's not the reason that we have global warming, right? D is is the best answer here out of all these. In a nuclear fission reactor, the moderator. They love asking about the moderator. And what is the role of the moderator? It needs to slow the neutrons down to increase the chance of fission occurring. Okay, so to make the chain reaction more likely. Okay, so Stefan Boltzmann's law, right? So we have these black body curves here, and yeah, so they have the same surface area and so on. Now what you should really notice here is that we have these two peaks, but those two peaks, they seem to be sort of at the same wavelength. Well, that means the temperature can't be different, because the peak wavelength depends on the temperature, right? It's inversely proportional to the temperature. So the temperature cannot be different. We have equal temperatures here for X and Y. So, you know, these two curves are due to the emissivity being different, right? So remember, a black body intensity is simply sigma times absolute temperature to the power 4. But, black bodies don't really exist. We can only... real objects, they can be modeled by sort of some factor E between 0 and 1. How close is it to being a black body? And you can see Y is less of a black body than X is, right? So we have different emissivities but equal temperatures. Okay, simple harmonic motion, total energy. So we know that the total energy can be written as half m omega squared amplitude squared. So what's the total energy now if the period is changed to 5t? So period is 5 times as long. So same amplitude. Okay, well, we know that omega is proportional to 1 over t, the period. So if we make the period 5 times longer, then omega is going to be 5 times smaller, 1/5 of the previous omega. And we can see in the total energy that we have omega squared, so the total energy is going to be 25 times smaller than the previous total energy, and 1 over 25 is 0.04. So A is the right answer. Colors seen in oil slicks. Okay, still topic 9, high level, thin film interference, of course. Colors in oil slicks. This is the thin film interference phenomenon. Two-source interference, identical sources dipping in phase into water. Along which of the label lines is the difference in path difference from the two sources equal to 2 wavelengths? Well, we know right in the middle we have 0 path difference, right? And then at A, where we have our first maximum, there we have 1 full wavelength of a path difference, and at C we have 2 full wavelengths of a path difference, right? So 2 wavelengths is C. At B and D we have 1.5 and 2.5. We have destructive interference at B and D. In order that the light from two... Okay, yes, so we only get an interference pattern when the light is coherent, right? So remember that means a constant phase difference. That is what will produce an interference pattern with light. So we don't necessarily have to have point sources. Doesn't necessarily have to be monochromatic. You can have multiple wavelengths being emitted, and they don't have to be of the same intensity, but the coherence is a very important condition. Doppler effects, still topic 9. Train travels towards you. So we sort of have a moving source that always looks like this, right? Moving source, US. We have the sound is still just moving with a speed v. And we have an observer over here waiting for all those to arrive. Now, why is the pitch louder? Because the wave fronts reaching you are spaced closer together. That is what's happening. They're not traveling faster towards you. They're still just traveling with the speed of the wave in that medium. They're not spaced further apart, definitely, and the sound frequency emitted by the whistle changes with the speed. So the last answer is correct, but it's not explaining why you hear a different pitch. It's just stating that you hear a different pitch, okay? So B is correct. Topic 10, gravitational potential. So remember, gravitational potential is a scalar quantity, a scalar function that we can just superpose, just add together. Scalar that superposes, okay, follows the law of superposition. So at point P, I can just work out the potential due to one mass, and I can add the potential due to the other mass at that point. And because we're right in the middle there, we get this, and that adds up to this, which is B. 34, Coulombs law. Another classic from, I don't know, 2005 or 2006. I've used this many times on tests. Two charged plastic balls. Okay, so they're in equilibrium, so that means we sort of have weight is being balanced out by the Coulomb force, QQ over D squared. Now, if the charge on each ball were doubled, okay, so the charge doesn't necessarily have to be the same, but if they're both doubled, then we know that the numerator goes up by a factor 4. Okay, but then, you know, the weight doesn't change, stays the same. So in order to get a new equilibrium, we need the Coulomb force to be reduced again by a factor 4. So doubling the charges increases the Coulomb force by a factor 4, so it starts accelerating upwards. But then when the distance is double, we get double distance squared, which gives us a factor 4 in the denominator, cancels out the extra factor 4 in the numerator, and we get the same size Coulomb force, which again can balance out the weight that hasn't changed. So it's 2D. Okay, here we have also topic 10, so the electric field between two metal plates, change in potential over change in distance. And so here we have sort of a constant EMF applied across the plates, and the distance is D. How does the electric field strength vary with D? Well, that's of course just inversely proportional, inverse proportional relationship. Okay, which one of the following lists the three classes of fundamental particles? Well, we know there are leptons, we know there are quarks, we know there are exchange bosons. That's really it. Okay, so hadrons are not fundamental because they're made of quarks. Okay, mesons are not fundamental, they're made of two quarks. And baryons are not fundamental, right? And yeah, what else can I? Yeah, hadrons and baryons and mesons are all not fundamental. Okay, it's A, clearly. The Bohr model, good old Niels Bohr, predicts, what does it predict? It predicts the wavelengths of the principal lines of atomic hydrogen. So he, you know, really worked out the hydrogen atom, how that, how we can explain the spectrum, the emission spectrum we get from atomic hydrogen. So his model didn't work on multi-electron atoms. That's one of the reasons they had to develop, you know, quantum mechanics fully. So he didn't look at molecular hydrogen. His model didn't work for that either. It also couldn't explain the relative intensities. So it's just B. Okay, photoelectric effect. We have a work function of 3. Photoelectrons maximum kinetic energy 1. So we know that the energy of the photon was 4 eV. Now, if the frequency of the radiation is doubled, we know that energy is proportional to frequency. Then now we have a photon energy of 8 eV. And if still 3 eV is used to knock the electrons out, then we have a maximum energy of 5 eV left over. Which phenomenon provides evidence for the wave nature of an electron? That is, what were they called again? I can't remember. Görner. Oh, yeah, can't remember the name. Would have to look it up. Germa and something, can't remember. Okay, but it's electrons being scattered by, you know, by the tiny spaces between atoms in a crystal. Okay, so that is what provided evidence for the wave nature of an electron. Gave the Nobel Prize to those people. So the line spectra of atoms doesn't really provide evidence for the wave nature of electron. It's more like this is the discreteness of the atom, right? Of atomic energy. So the discreteness of energy in the atom. That's what A is. The photoelectric effect is sort of the particle nature of photons. You know, this is sort of showing that light can be actually thought of as a particle, and the beta decay of nuclei really just has something to do with, you know, new forces being present in the nucleus. So the direct evidence for the wave nature of an electron is the scattering that happened. Was it in the 20s, 1927, something like that. So, okay, radioactive decay, almost there. Sample of radioactive isotope, same initial activity, so AX equals AY. Now we know that activity is proportional to the number of radioactive nuclei, so I would write this very important formula: A equals lambda n, super important, always true. Nx is twice ny, and remember that the decay constant is inversely proportional to half-life, and if nx is 2ny, then ny cancels out. We have a factor 2, ln 2 cancels out. We can see that ty is going to be half tx. So if half-life of x is t, then we get 0.5 t. Okay, 40 marks. I hope that was fun, because it was definitely fun for me.